Kalam, who was then with ISRO, came to DRDO, and then he ignited the development of what is called as the first major program for development of defense technology in a large scale, which was called as the IGMDP, which is the Integrated Guided Missile Development Program. So there was a slew of 5 different missiles, Agni, Prithvi, Trishul, Akash and Nag, which were developed by DRDO at that point in time. And the thrust here was not just on development, it was on developing them indigenously, using resources from within the country. And the thrust was on system development. Earlier, the idea was to do basic science and technology, do a little bit of applied science, make technologies, and then take the help of foreign countries and then integrate a system. But here, with the IGMDP, India took on the role of system development with due focus on modern project management practices. So initially, there was a lot of skepticism whether a developing country like India can take on development of missiles at such a large scale. But then within a few years' time, within 10 years' time, we actually delivered what was promised, and then the world started taking notice. And India came into this big league of countries which had our own missile technology. Technologies that we have to send armaments to any part of the world today. So after Dr. Kalam, he was still in the country, he was the scientific advisor to the principal scientific advisor later. So then what happened was, because of the culture that he had brought in, a lot of systems in various domains started developing. So we had the LCA Tejas, light combat aircraft coming up. The program was sanctioned in 1993. We had the main battle tank, Arjun, MBT Arjun as we call it today. All of them getting started with suite programs. So we also took efforts to bring in Indians who had bigger exposure to these technologies outside the country. They were brought back, people like Dr. Kota Harinarayana, people like Dr. V.K. Atre. And then we had combined programs for the Indian Navy, for the Army and for the Air Force. And we also looked at developing enabling technologies for ensuring that we the system. And by this time, DRDO has grown into a large setup of more than 50 laboratories. Project management practices. And these laboratories are clustered into domains for easy administration. And then this was a period when India was counted among the technology leaders, at least in the area of defense technology. Take on development of missiles at such a large. Now there is one pertinent question that we need to address here. Why really do we need defense technology? I remember around 10 years back, I was assisting set of students in one of the schools in our city. And there was this young boy who got to ask me, like, you are doing a technology, you are doing inventions as a scientist probably, but then you are making something destructive. You are doing things for defense. Is it really required? Why can't you concentrate your energies on something better and useful for the society? Now, I was a bit taken aback by this question. But then, fortunately, I remembered what Dr. Kalam had told us when he first addressed us as young scientists when we joined the organization. That for a country to be respected in the world, it is required that we have enough strength in our armor. So we have only strength respects strength. So if you take the case of human development of mankind, we find that we have been had lot many warfare across the years. Our the whole history of human civilization has been a series of wars across the centuries. So basically, it's about somebody having might trying to control of somebody else, trying to make a bigger country or civilization, whatever. So for any country in the modern world to be independent, to be strong, we need to have a very sound defense technology. Now, only if we have a sound defense technology strength can we be economically strong. Because then only can we actually start developing our own industries in the way we want it, without the fear of being taken out by somebody else. Before independence, India was probably, let's say before the advent of the colonialists, India was probably one of the richest countries in the world. But then look at our state after years of colonization. When the British left India in 1947, what was left was of a country which was actually one of the poorest in the world at that point in time. So to boost our economic strength, it is essential that we should be strong in terms of our own military affairs and our own technologies. And also, in developing different technology, we also need to develop economic strength. So it basically boosts industrial growth when you make technology in the country, when you indigenize them. And also we ensure that the technology has a life cycle support within the country. So let's say you import an aircraft from, let's say, France, you are also dependent on France for all the subsequent product support which are also costing. And then you pay huge sum in foreign exchange from the taxpayers' money. Another issue is when you import, there's a huge cost involved, and which is sometimes very, very prohibitive. An example I would like to tell you is that of our current aircraft carrier called INS Vikramaditya, which was in fact what do you call it? It was actually a ship which was basically brought in from Russia. So we bought it from Russia, and at that time it was called Admiral Gorshko, that was the aircraft carrier. So it started with something like 7,000 crores, and finally when the ship came here, the cost went up to 70,000 crores of rupees. So that's a huge investment, and Russia knew that we didn't have this technology. So it's like whatever they're willing to offer, we have to take. That was the sort of situation there. There is also a large political and strategic role in terms of defense technology. So currently, we do have still the stigma of being the biggest arms importer in the world. I think we have just taken the third place now, but at one point in time, we were the biggest arms importer. And then that is one problem. The second thing is anything that you import, there is a likelihood that this supply can get switched off during wartime. So depending upon the geopolitical influence that we have on the supplier, we cannot really ensure that we have the steady flow of technology. Also compounding the problem is the issue of technology denial. So when we started developing the missile technology, there were many critical components which were not given to India, and they were called as denied technologies. So there were missile technology controlled regimes which prevented other advanced countries from giving us these technology because they didn't want us to develop. So for example, there was something called as a servo ward, electro-hydraulic servo ward. It's a very small component, but which is very essential for any missile to perform. So this was not available in the country, and then so DRDO took up the task of developing that technology indigenously. And today we have our own system where we not only make these servo wards, but we also export them. The other thing is, the demand for non-vulnerability. To explain this, let me take the case of another organization called Center for Department of Telematics, CDOT, which many of you will be familiar with. So at one point in time, India was at the forefront in terms of telecom technology. So we have our own indigenous technology. In fact, we were one of the few technology countries in Asia to be the pioneers in terms of telecom switching technology, etc. But then there was a time when a lot of foreign countries with their companies flooded our markets with telecom technology, which then stopped the development of technology within the country because of course competitiveness and issues like that. And within a few years time, we realized that we had missed the bus and we were hugely dependent upon foreign countries for this. So this demand for non-vulnerability is a very, very important issue. And then the last point that I would like to bring to you is something called as Trojan horses. I hope many of you are from the software engineering side, being from the Department of Computer Science. So many of you would know what exactly Trojans are. But especially when you have a software-based system, we really have to be careful about Trojans. So just to give an example, let's say we have an electronic warfare system, which let's say we buy from Israel in the country today. And Israel incorporates a sort of Trojan, which is like a software activated command based on some RF signal, which says that, once we start doing a war or something, if they send that signal, our equipment stops working, or it may work in an altogether different way. So imagine if they have this particular Trojan and they sell the rights of this Trojan to our enemy country at probably 5 or 6 times the cost of what they sold as the technology for. So there is a business element there which a country would like to do. And then, so we have to be really careful when we buy such systems. So unless and otherwise we actually indigenize our own technologies, make them within the country, we are liable to each of these issues. So today, fortunately, because of the efforts that has been there in the country, the defense technology, we have been pursuing excellence at a large level. And today I'm proud to say that I'm part of a fraternity in India where we are one of the global leaders in defense technology. Today, India is one of the 4 countries in the world to have its own airborne early warning and control system. We are one of the 5 countries to have our own submarine sonar suits. We are one of the 5 countries to have our own 4th plus generation aircrafts, fighter aircrafts. One of the 5 countries to have our own ballistic missile defense. One of the 6 countries to have our own nuclear-powered submarine. One of the 7 countries to have our own main battle tank. And one of the very few countries in the world to have our own electronic warfare program. And probably one of the very, very few countries in the world to have really inducted and operationalized a supersonic cruise missile in the world today. So all this has been done in the country, mostly because of the efforts of DRDO, Defense Research and Development Organization. But it's not just DRDO. There's a huge economic, there's a network which involves the industry. We have a large set of industries all across the country, and also academia. Now you would ask me, like, how is academia, how is a college, or let's say a university involved in defense technology? Now, I mean, there are many colleges or universities in the country today who have been contributing to the defense at a steady pace. I'm not sure how many of you know that for the Agni missile, one of the most critical algorithms is basically the control trajectory algorithm, which is the crux of the control of the missile. And this particular algorithm was actually developed by the faculty and students at Jadavpur University in Calcutta. So similarly, there are many other areas. Like for example, in our I'm working in Naval Physical Oceanographic Laboratory in Kochi. We have almost 30 academic institutions today working with us in developing various technologies, sometimes doing basic research and fundamental research as well. As you can see from this slide, today DRDO has a set of 52 laboratories all across the country. And in Kerala, we have just one laboratory, that is Naval Physical and Oceanographic Laboratory. As such, in DRDO, all these 52 laboratories are clustered into 7 different clusters. So these are called technology clusters, and all of them are commanded by a Director General who reports to the Chairman DRDO. So we have the Aeronautical Systems Cluster, we have the Armaments and Combat Engineering Systems Cluster, we have the Microelectronic Devices and Computational Systems Cluster, we have Electronic Systems Cluster, Naval Systems and Materials Cluster, Life Sciences, then we have Missiles and Strategic Systems Cluster. So NPOL comes under the Naval Systems and Materials Cluster. In fact, in the Naval Technologies domain in DRDO, there are 3 laboratories which work in naval technologies. One of them is in Kochi, that is NPOL. We have a sister laboratory called NSTL, Naval Science and Technological Laboratory, which is situated in Visakhapatnam. And the third one is called Naval Materials Research Laboratory, which is located in Mumbai. Now, I don't know whether you noticed that there is a similarity between these 3 places, Kochi, Visakhapatnam, and Mumbai. So all of these are actually locations where we have the naval commands situated. So in Kochi, we have the Southern Naval Command, and Vizag, we have the Eastern Naval Command, and the Western Naval Command is in Mumbai. So I'll just tell you briefly about NPOL. We work on something called sonar systems. I'm not sure how many of you really know about sonar, but I'm sure everybody would have really heard about what a radar is. So simplistically speaking, a sonar is like a radar working in water. So radar works on electromagnetic waves, whereas sonar works on acoustic waves, that is sound waves. And today we have a slew of sonar systems available in the country, thanks to the effort of NPOL. So we have sonars which are installed on ships, we have sonars on submarines, we have sonars on based on helicopters or other aerial platforms. We have sonars which are off-board systems, which are not dependent on any platform, so to speak, but that they can be independently positioned on the seabed or from a jetty or a harbor. Now, generally speaking, a sonar is not a single unit. Now, just to illustrate this fact, I'm taking the case of a submarine sonar. Now, as you can see here, in a submarine sonar, you can actually call it as a system of systems. Because in this figure, you can see there are many types of sonars all around the submarine. In fact, a submarine constitutes 40% by volume of all the electronic equipment that is available on board the submarine. Almost 60% of the electronic wiring in the submarine is basically for the sonar systems alone. So you have different types of sonars, one for passive surveillance, then you have a sonar for active surveillance, you have underwater telephony, you have intercept sonars for intercepting signals, you have obstacle avoidance sonars so that you don't you don't hit anything in the path, because once a submarine is underwater in a dive condition, you can't see anything. You are totally sitting in a dark room and you depend on your ears to move forward. So the sonars can be called as the eyes and ears of the submarine. I don't know whether you have read about it, but a few years back, we lost a military aircraft, right? There was an AN-32 aircraft which took off from the military base in Chennai. It was carrying supplies to our base in Andaman, and then somewhere in the Bay of Bengal, it had some problem, and the flight actually fell down into the Bay of Bengal. And around 1 year before that, we also had this case of the Malaysian Airlines flight, actually falling somewhere down in the Indian Ocean and not being recovered. But this military aircraft was actually within 3 days we could actually find out where it was. Now, that was a big news at that point in time. I think it happened in 2018. Now, this was actually detected by this submarine, our Indian submarine. It was carrying the Indian sonar. So the same intercept sonar in the submarine actually intercepted the distress signals which came from the distress box of the aircraft, and we could actually intercept those signals and rescue, or let's say salvage the aircraft at that point in time. So this is something which speaks volumes about the capability that India has established in sonar technology. So when you talk about sonars, again, let's talk about engineering. Now, what exactly makes a sonar, or what aspect of engineering do you have to learn to make a sonar? I'm basically a mechanical engineer. So when I joined NPOL, I was like wondering, I know nothing about sonar. How do I really get into it? But then I found out that sonar is not a subject which is taught in schools or colleges, and it is actually a multidisciplinary area. So you have engineers from various disciplines, not only engineers, you have people from the basic sciences also working on these systems. So we have people from oceanography, we have people specialized in power electronics engineers, we have computer scientists working on simulation, we have the material scientists, materials engineers, we have mechanical engineers working on the wind and handling systems and structures, mechanical engineers and physicists working on transducers, we have electronics engineers working on signal conditioning and signal processing as well. And then a lot of people who studied computer science and electronics as well, working on the human machine interfaces and the displays. And then people with mathematical statistical capabilities, working on signal processing algorithms, and a whole set of oceanographers from the physics background or oceanography background, working on the oceanography aspects of the sonar. So today in the country, we have, for the last 30 years, we have a record of having made no imports in sonars, especially when you take the case of hull-mounted sonars. So today we have hull-mounted sonars, torpedo defense systems, torpedo sonars, variable sonars in the country for ships. As far as submarines are concerned, we have sonar suits, we have acoustic domes, and we have distress sonars. And then from aircrafts and helicopters, we have dunking sonars and sonobuoys. And then we have got seabed arrays and diver detection systems, which do not necessarily require a platform to deploy. And not only this, we also developed a set of systems like underwater communication systems, noise measurement systems, array calibration systems, noise making systems, directing gears, expendable weighted thermographs, and a lot of other sensors for oceanographic applications, all developed by this laboratory in the span of, let's say, the last 30 years. So let me try sharing a video now, and let me see if we can listen to that video. So depending on the bandwidth issues that we have here, let's try that. So let me try sharing this video. By the way, were you all able to listen to the see the slides properly? Just a feedback from your side, anybody?
Yes, sir.
Okay,
It
good.
was visible.
Okay, very good. So what I'll do now is I'll try to open this particular video for a break, and okay, let me see whether the video is visible.
Sir, I think your sharing is stopped.
Yeah, could you come again?
Not yet.
Oh, sorry. So let me once again try that. Okay, so
Yeah, we can see the screen.
Is it visible?
Yeah.
Okay, good. Okay, so that was the video. I mean, basically, I just wanted to show you what are the possibilities that we have for sonar development, the various technologies involved, the various products which are made, and the various test facilities that we have set up for developing these things actually. So I hope you could see the video properly. So let's go back to the presentation now. So are the slides visible now?
Yes, sir. It's visible.
Good. So let's go ahead now. Now let's go ahead and look at what exactly is the various what we call disciplines of engineering which get involved in defense technology. As I said earlier, defense technology is actually an area where various facets of engineering disciplines come into play, and technology is nothing but application of engineering. So basically, in the next few slides, I would like to give you a glimpse of various facets of defense technology, and we could probably discuss upon how different engineering disciplines are involved in the development. So let's start with this slide. There's a question which people normally ask, like what is so special about defense technology? Ultimately, what you do are also what is being done by the same engineer in a civilian application, which might be true in many cases. For example, as shown in this cartoon here, the Department of Health in the civil setting actually calls an experimental. Hello, yes. Is the slide visible?
Yes, sir. It's visible.
Yeah, fine. So
Yes,
the Department of Health actually calls it as genetic engineering, whereas when you come to the defense, actually it may be called biological warfare. So what defines the defense technology from a civil technology is in terms of the application that we are looking at. So you have automobile engineering applications coming in for high-end passenger trains, or for aircraft technologies for high-end passenger aircrafts. You could have similar technologies coming in for defense, but with a viewpoint of warfare. So what really differentiates it is from the viewpoint of warfare. So let's take a look at how it develops. So I'm not sure how many of you really are into this idea or concept called idea pipeline. Some literature calls it as idea funnel, or some people call it innovation funnel. So what really happens in the research and development side is you start the research with a lot of ideas, okay, about a particular requirement. So let's say you want to make a product which meets a particular requirement. Let's say, for example, I'll take an example of underwater communication. So let's say I want to have a set which can communicate from a submarine to another submarine, let's say 100 kilometers away. So you're looking at various solutions. So we'll come up with a lot of ideas. People ideate first, and then you do what is called as proof of technology. So you try to find out the technology blocks which are involved in creating that particular product or system, and then you try to make one prototype. And then after making the prototype, you do a proof of concept study. So you really take it to the field and you try conducting experiments with that proof of concept product, and then come up with the results. And then you find that not everything is working. So then you start reworking on that. Then finally you come to one system design which will really work at all costs. So you go ahead and make a pilot product, which will be a product ready in all aspects other than its what you call full-fledged production issues. And once that is ready, once the pilot product is ready, the technology for the same is transferred to the engineering side of an industry to really produce it. So normally what happens is from a designer or from a scientist in a research laboratory, when you come to a production engineer at the industry, so this could be anybody. So the scientist could be a mechanical engineer, and the production engineer also could be a mechanical engineer in the industry. The developer could be a software developer or R&D scientist here. It could be a software engineer in the industry who is trying to actually look at the other aspects in terms of networking, software keys, etc. So basically, both these sort of people have totally different skill sets. So you look at scientists, they are innovation oriented, whereas the industry guys are mostly procedure oriented. So their focus is in getting out a product and selling it quickly. So the interests between the two are always conflicted. So if you look at the role of R&D, the primary interest would be for an engineer to do a basic research, to develop technologies, to carry out system design, develop the system, carry out field evaluation, and then do the technology transfer to industry. He's not worried about the commercialization aspects. Whereas when you come to the industry, there's a lot of market involvement involved. And so they are the people who absorb the technology. They then engineer the system in terms of quality and reliability. They productionize it in terms of making production grade systems in a lab scale. And then they also have to provide lifecycle support for the system once it is being used by customer. And then they have to give a feedback to R&D for any additional things which are done to be by the R&D in the further variants of the product. So when we talk about converting a civil thing to a defense product, there are certain characteristics which actually define the technology. So let's take an example of a ship. So a normal ship would have you would have a hull, you would have the accommodation units, you would have the basic propulsion units and things like that. And it may be used for any civilian application. But then to convert a ship to a warship, you need a lot of other technologies. So you need, let's say, hull-mounted sonars for surveillance, you have underwater communication systems, you have variable sonars, you have a variety of SATCOM terminals, electronic countermeasures, inertial navigation systems, then various types of transceivers, both UHF and VHF, radars, and things like that. You also have a large set of weapons. You have torpedoes, you have torpedo defense systems, you have missiles, you have guns, missile launchers, and then you also have a combat management system to actually convert the data or information that is picked up by each of the sensors into an action to be taken by a weapon happening automatically. So this is how you convert a ship to a warship on a very simplistic scale. So if you look very carefully, when we talk of these technologies, essentially there are three things you can see which define the whole system in terms of a defense technology. First is a platform itself. So you have a platform or you have a system which you convert to defense application. So it could be readily available or it could be a totally new design. Second is you have a lot of sensors to actually take information. And then you have a set of weapons to actually take action in terms of countering an adversary or maybe even inflicting damage, etc. And then lastly, you also need something called as a communication network to ensure that all of them are working in a synergistic manner. So four things: you have platform, you have sensors, you have weapons, and you have a communication network, which finally convert a particular system to a defense system. And quite often, the engineering of a system is dependent upon the strategy that you adopt for its operation. I'll give you an example from my domain of activity, that is naval warfare. So here, let's see this slide. I hope this slide is visible properly. So first of all, let's say submarine comes up. Okay, so we are working in an area where a submarine, we should detect a submarine and take immediate action. Any submarine which is not submarine announcing its arrival. So any submarine comes with a hidden agenda of either surveying our area or inflicting damage in our area. So we are equipped to detect it. So the moment the submarine comes, it's quite likely that one of our ships which has a hull-mounted sonar detects it using acoustic signals. But then the hull-mounted sonar has limitations because the ship itself makes a lot of noise and you may not be able to pick up the submarine. So it's like you are sitting in a room at night and outside it is very dark, but your room is fully lit. You have all the lights on. When you look outside, you can't see anything. But a person standing outside in the dark can see everything inside the room through a window, which is open. So similar scenario. The submarine will be able to see us, but the ship may not be able to see the submarine in the same manner. So what this ship does is, it deploys another sensor called a towed array sonar or a variable depth sonar, which actually moves away from the ship, away in the sense like say 200, 300 meters away from the ship, and then it starts sending acoustic signals and listening to the submarine. So it fairly tries to keep a track of the submarine and then sends a quick signal to the base station to send a quicker means of detection. So it sends a maritime patrol aircraft which comes to that area roughly, and then it tries dropping what is called a sonar buoys. So these are small units which are dropped. They come with the parachute. Once they hit the water, a float opens up and an acoustic package drops down. And this acoustic package in the sonar buoy is actually a small sonar which then tries to listen to the submarine and track it properly. But then sonar buoy has a limited life. We have to keep on drawing submarine sonar buoys. So you send signal for a ship to for a ship or a base station to send a more sustainable system in the form of a dipping sonar, which comes from a helicopter. So helicopter takes time to reach there. So the first the aircraft comes, it deploys the sensor, then slowly the helicopter comes, and helicopter can hover in that area. So it can remain in the area close to where the submarine is, and then start detecting the submarine properly, and then also take action. So once you confirm it is a submarine, both the helicopter and the aircraft start sending out torpedoes. So what does the submarine do? The moment the submarine knows that it has been attacked with a torpedo, it launches a decoy. So this decoy then tries to create a counter noise and then tries to protect the submarine from being attacked by these torpedoes. And the submarine also, in its eagerness to get away, it tries to fire a torpedo against the ship which is in the vicinity. Now the moment the ship gets the knowledge about the torpedo, which can be detected much easily because it makes much larger noise, it can be picked up by the sonars. So the ship also fires a decoy to ensure that, or let's say series of decoys to ensure that the torpedo does not come and attack the ship. And then immediately the ship also launches a counter-offensive in the form of a torpedo to really attack the submarine. So now the submarine is attacked by the ship, the helicopter and the aircraft, all of them launching torpedoes, and you have an area where it is cornered from all sides and finally is killed. So now this is basically the operational requirement. Now if you see here, to get this thing done, you have all these elements that I mentioned earlier. You need different platforms. You need different sensors to pick up the data of the adversary. You need different weapon systems to actually take action against this adversary. And you also need a communication means to actually communicate between all of these elements. So that is where the role of engineering comes, in making the platforms, in making the sensors, in making the weapons, and in ensuring the communication system. So let's now proceed to look at various facets of defense technology and how engineering is an integral part of these technologies. Let's take the case of missiles to begin with. So in missiles, there are many technologies like integral ramjet rocket engine, which is basically a propulsion technology. So this is an area where mostly we have mechanical engineers working, we have chemical engineers working, we have instrumentation engineers working, and this is an area where you have simulations done and you have a lot of computational fluid dynamics. So to some extent, even computer science engineers are involved in that. Then you have an area called multi-target tracking, which is an area where mostly electronics engineers and computer science engineers are involved. Then you have homing guidance using seeker. Again, in an area where instrumentation engineers, electronics engineers, electrical engineers, and computer engineers work. There are a lot of radars which are network. Again, communication engineers and electronics engineers. You have radomes, basically which are structures which can, protect the radar and also ensure that the sensors can listen to the signals, whereas you also protect them from being any other external agency. You have re-entry devices, like when you have a missile like Agni, which actually is fired from our base ground, it actually goes outside the atmosphere, and then finally when it re-enters the atmosphere, there's a huge amount of thermal load, and you will ensure that the missile does not get burnt out. So you have a re-entry device which actually ensures that the missile re-enters the particular atmospheric, barricade in a much smoother manner. So this is an area where again mechanical engineers, chemical engineers are all involved. Even some amount of work is done by civil engineers in this area. Then you have control fins, where a lot of guidance and aerodynamics are involved. So you have aerospace engineers, mechanical engineers, and electrical engineers. And then you have warheads, which are mainly done by chemical engineers and material scientists as well. And all these missiles that you see here today in India, like Dhanush, Prithvi, the BrahMos missile, which is done in collaboration with Russia, or the Agni or Akash, all of them have all of these systems that I mentioned about. Moving on to armaments technologies. So similarly, here again we are talking about rifles like INSAS, or you have heavy alloys penetrators. So you have penetrants which are basically capable of creating large amount of kinetic energy, which can penetrate heavy alloys also. Then you have multi-barrel rockets like Pinaka, which is shown in the figure on the left bottom. Then you have bombs and warheads like the 450 kg HSLD bomb, which is shown here. Then you have explosive reactive armor. You also multi-mode grenade. You could even have smart bombs like the SAW, that is smart airfield, anti-airfield weapon, which is basically a bomb with the capability to detect the target and log on to it. So anything within 100 meters can be engaged correctly. Then you have towed artillery guns like attacks, which are large guns, like the howitzer sort of guns, which can be taken to the battlefield, and they keep on firing at a much larger rate and inflict damage upon the adversary. So these are areas where probably mechanical engineers are involved, chemical engineers are involved, civil engineers are involved, and especially when you come to the instrumentation part, electrical engineers and electronics engineers get involvement in these areas. When you come to the aeronautical systems, all of us know about the LCA Tejas, which is the pride of the country. In fact, we are the only country in the world to have developed a 5th generation fighter aircraft, starting from the 4th generation. Everybody had a series of historical developments, whereas we started right from 4th generation and they did a 5th generation with whatever we could gauge from our knowledge. And we definitely took a lot of time and a lot of money also, but then today we have this capability. So when you come to the area of aeronautical systems, you have avionics, which is basically aeronautical electronics, you could say. So which is an area which is predominantly involving electronics engineering. And when you talk about the aircraft itself, you have electronics, mechanical, aerospace, structural engineers, computer scientists, everybody involved, computer engineers as well. The more model-based data fusion where predominantly computer science engineers have a role. Then you have recovery parachute systems like heavy drop systems I showed here. This is basically for deploying, let's say if you want to deploy a tank in, let's say, in Ladakh, in the mountainous area, you can't actually take a tank there. So all you can do is take them, carry them in a big, aircraft like a C-70 carrier. Drop them. This heavy, which can drop. And then you have unmanned aerial vehicles like Black. And then you also have this huge avionics moved on the airborne early warning control system. So a lot of automation, etc., and control, which is again brought in by a lot of electronics engineers and instrumentation engineers working in tandem. Moving on, when you move into the area of electronics warfare, this is again one distinct area. You have a slew of radars in the country today. Radars which are fitted on ships, on submarines, on aircraft. You have aerial radars. You have two-dimensional radars. You have battlefield radars. You have portable radars. So what I've shown here is a portable radar. It's called Bharani. It is a two-dimensional, low-level lightweight radar. And so all these sort of radars, basically, they involve and a lot of electronics. Engineers are involved. Electrical engineers are involved in the cameras, thermal imaging systems, laser devices. Especially when you talk about today, we have this thing called directed energy weapon. So let's say, recently DRDO has developed the anti-drone system, which has a jamming facility which can jam a drone so that it loses its control and it's stuck in that area. And then you have a directed energy weapon in the form of a laser, which is basically a pulse laser in a very high directional energy, which focuses the energy onto the drone and burns it. So these are systems which have been developed in the country. And if you look at any other electronic countermeasure system, electronic support system, or the ECCM systems, all of them involve primarily electronics engineers working in tandem with mechanical, electrical, computer science engineers, etc. When you move on, combat vehicles, we have a lot of civilian vehicle applications in terms of automobile technology. So whether it is gear drives, powertrains, the combustion technology, etc., everything is available. But then when you convert them into a defense system, it's an altogether different ballgame. So today when we talk about a battle tank, let's say we have MBT Arjun, which is the main battle tank. We have many other set of tanks like bridge laying tank, etc. All of them involve a lot of mechanical engineering, a lot of guidance engineering. So you have a lot of electronic systems also inbuilt. You have a lot of sensors. You have a lot of control and guidance algorithms built in. And then there are things like bridge laying tanks and amphibious floating bridges, where a large amount of civil engineering is involved. And then you have mine clearing equipment, mobile bridging system. Again, a lot of area where civil engineers have a role to play, including avalanche control structures. And then mobile shelters. So you have, let's say, when you have a biological warfare or a nuclear warfare, or maybe even chemical warfare, you have shelters to be built in an area for quick, protection of people. So there are mobile shelters and immobile shelters, both of which are made by civil engineers working in tandem with nuclear engineers and chemical engineers, etc. Today we see a lot of autonomous systems happening in defense as well. Today in the commercial zone, we have a lot of drones, even for things like wedding photography. But then when you come into, these are things which are actually spin-offs from defense research. In fact, autonomous systems have begun their conquest first with defense systems and then slowly moved out to the civilian sphere. So when you look at a drone, we have the Netra used for surveillance applications. There are a slew of remotely operated vehicles. I've shown the ROV Daksh in the picture here, which can go and remove explosives from areas where humans cannot go. We have unmanned underwater vehicles. We have unmanned ground vehicles. Unmanned underwater vehicles are rather called autonomous underwater vehicles, or AUV. Then we have things called mini mule. So mule is a robot which is almost like an animal, which can operate almost like an animal operates in a different terrain. So these are things which are really available in terms of robotics engineering. So today in DRDO we have Omni exports snake robots. These are small things which look like worms, which can be used for espionage or related activities, or which can go into closed crevices, etc., and then monitor either using audio sensors or video sensors. Then you also have huge things like robot sentries, which are tracked vehicles which can actively work in an autonomous mode and then collect information, do mapping of area, etc. So these are areas where many fields of engineering, like electronics, computer science, mechanical, robotics, all of them come into play. When you specifically talk about computational systems, in fact, computational systems are there in every facet of defense technology, but specifically the areas like speech coding techniques, cryptography, computerized war games. When you talk about image processing, especially satellite image processing, then when you make displays and human-machine interfaces, for example, the picture on your right is actually a sonar human-machine interface, wherein the information is presented to the user both in video and audio forms. And when you talk about secure networks for defense communication, simulators like the sonar simulator I've shown below, all of them involve a lot of software-related capabilities which are built in by the computer science engineers. Interestingly, engineering has a role to play in life sciences technologies also, especially when you talk in terms of defense, when the troops or soldiers are posted in high altitude areas like in Leh, Ladakh, etc. There are things like high altitude farming, for which a lot of techniques have been developed by DRDO labs in those areas. Then techniques and aids for making people comfortable in such climatic conditions where pressure is minimum, temperature is very low, etc. So you have hypo chambers where one man can stand in, he can survive for a long period. Then you have a CBRN force for nuclear protective clothing, biological warfare, radiation, chemical, etc. You have water treatment kits, stress analysis system, basically psychological analysis using computer aids. Then you have disease diagnostic kits. So today, let's say you have a lot of kits available in the market for medical purposes. Let's say your kits for diagnosing anthrax, for chikungunya, for H1N1, swine flu, a lot of diseases. All of these are actually kits which are spin-offs from defense technology, which have come on in the market. So primarily they were developed for troops who are working in forward areas who do not have the provision of coming to a medical area, the quick, what do you call so many issues at the primary area itself. And when you talk about bio toilets, in areas where where climate is very, very cold and below let's say sub-zero temperatures like below -4 degrees centigrade, the problem is for humans to survive there, the human waste itself is a problem. It doesn't decompose. So then we created bio toilets for these applications. And today you will find that when you go to Kashmir, the Dal Lake, the boats there, the railways, the bathrooms in railways, many of them have used the same technology which is actually developed by engineers for defense applications. Similar is the case with biofuels also. Lastly, I'll come to naval systems. So I've already shown you the video of the sonar particularly. So we have sonars, we have sonobuoys. Then other things are like torpedoes, underwater communication systems. Then we also have air-independent propulsion systems. A submarine, when it goes in water, you have to remain submerged for a long period of time. So normally we have diesel submarines, but then diesel engines require oxygen to work, air to work. So they have to come up once in a while. Let's say after 14 days, the submarine has to surface. Now, if you have a mechanism to actually lie underwater for a long time, and the energy is the oxygen or the fuel is produced in the submarine itself, you have a larger endurance. So for these, we have the air-independent propulsion systems, which are basically based on fuel cell technologies. These are also available, and you can these actually enable the submarines to travel larger distances, lie undetected, lie underwater for a longer duration. And also when you come to stealth technologies, so which enable the submarine or the ship to be undetected by any other radar or sonar, you need stealth. So that is another area where engineers can contribute. So all of these involve, again, mechanical engineers, electronics engineers, chemical engineers, civil engineers, everybody. And you would be wondering, this particular slide that I'm showing you here is about food technology. But then what does food have to do with defense? So interestingly, we'll find that you have a lot of products in the market today, like you have this MTR ready-to-eat chicken biryanis, you have ready-made upma, pongal, whatever. All of these technologies, many of these, for example, if you take the back side of the particular pouch, you'll find that the technology has been transferred from a particular defense food research laboratory in Mysore, which is a defense laboratory working on food for the defense. So what was done was basically for people, for the soldiers in forward areas, they had to have food with them, and especially during wartime, they had to carry food with them. So they need food which can sustain for long. So these techniques of easily making an idli and sambar or chutney, which can be reconstituted in let's say 2 minutes, was developed, and the same technology was transferred to the civil population as well. So you also have things like milk testing kits. You have freeze-dried technology for mutton kurma. I understand that there is a food technology department in St. Kitts also. So you would be interested to know that things like food freeze-dried technology, the what you call hurdle technology, spray drying technology, etc. All of them are practiced in defense as well, and many advances in these technologies have been converted into products which are used by not only by our armed forces but also by the civilian population. And there are things like high energy bars, like the bottom figure shows a chicken bar, which is actually a small bar which can be eaten in, let's say, probably 1 or 2 minutes. But then this single bar will actually provide the same energy that you get from a full bowl or full plate of food. So the idea is to actually have energy, shortest time, especially when you are at the war front. So not only for defense applications, the engineering that is done in defense technology is also sometimes transferred for civilian applications. Many of you have heard of the Kalam Raju stent. So the same carbon fiber, technology which was used for for missiles, basically, they had used it for making calipers for lightweight medical applications and things like that. Today, when the country is passing through a large pandemic situation due to COVID-19, there have been many technologies which have quickly come into the market because of the spin-offs from the defense technology. So you have ventilators, we have medical oxygen plants, and you have microwave UV-based sterilizers, the oxycare systems, and even from NPOL we have made this IR thermometers based on technologies that use for XBTs, which are quickly transferred to a company like Keltron, for example. Then Medidu, then crowd monitoring, temperature monitoring, etc. All of them have been quickly realized because such technologies are available in defense technology, and all we did was to transfer them back to the civilian sector. The classic case is that of the medical oxygen plant, which is basically developed for the medical LCA pages, and today in many of the hospitals in the country, we have such oxygen plants set up in a quick manner. But the future, when you look at the future, the thing is, in modern day warfare, it's not just about the systems. You also need to network them. You need to multiply in terms of force. So you have to network these sensors within a platform, and then you also need to network various platforms so that you ensure high degrees of interoperability, and the information flow is also very, very fast. So these are the key characteristics for future warfare. And as is told by Admiral Rafet in the US Navy, information as a weapon is gaining huge importance. So the biggest breakthrough of the current flight in OEF and YF, the successful integration of intelligence with operations and using the network to get the right person at the right time in the quickest manner. So information is also quickly coming up as a weapon. So see this cartoon for the change. So this was recently, I come across this cartoon, during the Trump administration in the US. So this cartoon says that, how does the new defense system work? And one of the key defense persons says that it strategically intercepts and destroys the president's tweets before they are able to leave the airspace of the United States. So this is a classic example of information warfare. You are ensuring that your limitations with respect to whatever information is going out is protected before it leaves your airspace, so that a foreign country does not gauge the situation within the country. Fellowship and senior research fellowship, or if you are an MTech, you can even go for research associates, etc. You can register PhD as well. So when you are applying for research fellowships, it is specifically done for a specific area of technology. So let's say then you are under, so the lab which is working on cyber warfare would definitely advertise for junior research fellowships in that area. And when you apply to that particular laboratory, you would end up working as a junior research fellow in that laboratory. Now, this particular fellowship is a time-bound activity. So normally it is 3 years, you get extended for 1 more year. And if you register for PhD, you get a total of maximum 5 years. But after 5 years, your contract ends. But then once you do well in your tenure, there are chances that you get a chance to sit for the interview as a scientist and again get into the same lab where you were working earlier. So the chances of you working in the same area are higher in that case actually. So Ashwin, does that answer your question?
Yes, sir. Thank you, sir.
Okay. So Karthika has another question. Where are the labs of DRDO situated? Now I did show a slide somewhere in the middle of the presentation where I showed 52 laboratories spread all across the country. But on a summarized note, I would like to say that the majority of the DRDO labs are clustered around Bangalore, Pune, Hyderabad, and Delhi. And the rest of the labs are scattered like Chennai, Kochi, Tejpur, many other places like Agra, Chandigarh. So we have DRDO lab in almost every part of the country. But majority of the labs, especially labs which are working on missile technologies, are clustered in Bangalore. Labs working on electronics and around aeronautic systems are clustered around Bangalore. The missile labs are clustered around Hyderabad. Sorry, and then the armaments laboratories are clustered around Pune. The life sciences labs are clustered around Delhi. So that's the primary thing actually.
Okay.
There was a question by Indu also. So Indu's question is, can a chemical engineering student have a scope in defense sector technology? So the answer is a big yes, definitely yes, because as I mentioned in many of my slides, there are many areas where chemical engineers have a huge role to play. Whether it is the propulsion system for aircrafts or missiles, whether it's armaments, the explosives in the armaments, whether it's the materials used in sonars and stealth technologies, everywhere a chemical engineer has a big role to play. In fact, most of the laboratories in DRDO, I've seen recruiting chemical engineers at one point in time or other. So any other question? Somebody was asking in between, isn't it? Okay, yeah. So in between Joel, there's a question from Joel again. So how can one apply for internship at DRDO? So basically, it is basically given by the individual laboratory. So, like for example, at NPOL earlier we used to take BTech interns, but now because of some other issue, we have stopped taking BTech interns. But for MTech students, there's an internship scheme. So every year we ask the colleges to actually send across a list of students who are interested to do internship in NPOL, and then we do an interview. Basically, right now it is telephonic interview, and then normally the person who wants a student, the scientist who wants a student, will directly take the interview, and once he is convinced that the student is able to work with him, we will offer him an internship at DRD. So that is the scheme is there, but in NPOL it is currently only for MTech students. There might be BTech schemes in other labs of DRDO, but it's again an individual lab affair. So you will have to contact the individual laboratories. Incidentally, for information on any other laboratory, you can always log into www.drdo.gov.in. I'll repeat, www.drdo.gov.in. You will get the information, the contact details of every laboratory out there. Sometimes they advertise these internships in the website as well.
Okay, thank you, sir, for answering our humble questions. We'll share the other questions later. Now, I invite Ms. Alina, Vice President of AI Club, to extend the word of thanks.
This wonderful opportunity for all who have participated to this webinar on engineering applications in defense technology. It is organized by the Department of CSE and AI in association with CSI and I would like to thank our speakers, Mr. Samir Duas, scientist and group head of management, who has found time to grace this event and enlightening us with a valuable knowledge. His class was very informative and opened up to discover new defense technology using various fields of engineering applications. We are extremely thankful to Ranju Tadpa, the head of CS department. Their able guidance has always motivated us, and I thank for her continued support. I extend my gratitude to the management and the principal, Dr. Joseph Pinto. My sincere thanks to the chief of AI Club, and engineer Veena Ekuma, and the coordinator of CSI, engineer Hari, and the coordinator of IE, engineer Vidya Kaya. I would like to thank Tibin sir and Justin sir. A deep sense of appreciation for the student program coordinator, Aaron Abraham, and also my gratitude to all student members of AA Club and co-committee members. Last but not the least, I thank all the students who take part in this webinar. Without you all, this wouldn't have been a huge success. Once again, I thank you everyone for your valuable time. Thank you.
Well, thank you. It was a pleasure for me too. And a warm note of thanks to all the organizers and for the opportunity. I'd be happy to interact further later. You can always post your questions over WhatsApp or email. I'll be happy to answer them as time permits. Thank you.
Thank you so much, sir. I thank all the partakers for your cooperation in this webinar, making it an amazing event. Kindly fill the feedback form because certificate will be issued to those who fill the form. Once again, I thank you everyone for taking the time to be here today. Thank you.